What's that? We brought the weather with us for a talk on climate change, and I see you all wrapped up. Imagine outside. Okay, so this is an eruption in Chile earlier this year, and one of the things I'll be talking about is how volcanic eruptions affect climate because of the gases they emit especially. So this is a geological perspective on climate change more or less over the last 400 million years or so, which is quite a lot to cram into 40 odd minutes. So I'm just going to sort of take out some highlights, if you like, and just to sort of pepper and illustrate the story over that period. I've been interested in this, I suppose, since my degree in the early 80s, and then leading some policy on climate change for the UK Sustainable Development Commission about 10, 15 years ago, and I've kind of kept up with it since. So sort of bringing the old and the new together, if you like, is one of the things I'll try and do today. So the first thing that we probably need to cover when we're talking about climate change, the first word that we usually stumble over is climate. The second one is change, but we'll come to that in a minute. So Mark Twain's always a useful source of quotes for these sorts of things. Climate is basically average weather, but the question then is the average of what? And we know that there's a kind of an oceanic climate on the west side of Scotland and a more continental one on the east side. We can think about Mediterranean climates if we go on holiday and what have you. So there's a sort of spatial scale to climate, but there's also a time element to it. Geologists will talk about, and I will a little bit today, about a Carboniferous greenhouse climate which lasted about 50 million years, about 300 million years ago, or a Cretaceous, sorry, did I say Carboniferous ice house is what I meant. Cretaceous greenhouse, another 20 to 30 million years, about 100 million years ago. So there's a kind of time scale to this. And the time scale that's used in current climate modelling for the International Panel on Climate Change is a rolling 30-year time frame. And that's about the minimum that you can get away with. We'll be talking about time scales of that plus hundreds, thousands or millions of years in the next half hour or so. And really everything I'm going to say is on this slide, but I'm just going to sort of complicate it as I go through over the next 45 minutes or so. So what controls climate is the amount of incoming solar radiation. It's not much today. Most of that arrives in the equator and is distributed north and south to the poles by winds and ocean currents in particular, which is the distribution of the surface heat over the Earth, as I said, by ocean and atmosphere circulation. And so in that, the positions of the continents become quite important, because if you've got a continent blocking an ocean pathway, that influences climate in some fairly significant ways. And then the third thing, which I'll also talk about, is the composition of the atmosphere, and in particular, the amount of greenhouse gases in the atmosphere at any one time. So everything I say is really just going to unpack that in a bit more detail. This is a solar eruption with the Earth to scale, just to show you that the sun's quite big and eruptions on the sun are quite large as well. And one of the external factors that shapes climate over time is solar luminosity, which you can see by the red line on this graph has been increasing since the Earth was formed about 4,600 million years ago. And it's about 5% more now than it was 600 million years ago. So that's a kind of background factor that geologists need to take account of in thinking about climate. Particularly because if the Earth was cooler in the past, you can stuff more greenhouse gases into the atmosphere, and it doesn't necessarily make the planet terribly hot, because there's less incoming solar radiation at the time. Orbital factors also have an impact on climate, and this slide sort of summarizes them. I'll say a bit more in the next few slides. But the eccentricity of the orbit. If the Earth is has a circular orbit, then it receives more or less the same amount of heat from the sun all of the time. But the more eccentric it is, the less heat it will receive when it's further away from the sun. Okay? And the other two cycles here, the tilt of the Earth's axis gives us our seasons, and the precession of the equinoxes. Also, those two things influence the distribution of heat across the surface. So the eccentricity of the orbit shapes how much energy comes into the Earth, and the other two cycles here affect how it's distributed across the surface. As I say, there's some more slides in a moment just to illustrate that. So a less eccentric orbit, the beckons, if you like, the Earth receives pretty much the same radiation all of the time. Something slightly more eccentric, like Boris, at the extreme ends of the orbit, the Earth receives much less solar radiation, and more so with a more eccentric orbit. In truth, the orbit is only mildly eccentric. It's kind of pretty close to a circle, but the difference between its maximum eccentricity and minimum in terms of the amount of heat received by the Earth is about 23%. Okay, so that's a fairly significant factor, which we'll see in a moment, has an important influence on climate. The tilt of the Earth, as I say, I'm not going to go into this in any detail, but it varies over a time scale of about 22 to 41,000 years, and it influences the amount of heat and how the heat is distributed across the surface of the Earth. And the precession, which is effectively where the North Pole is pointing, also shapes the distribution of heat across the surface. And all of those orbital factors interact to produce ice ages over the last 2 million years or so. This is just the last 400,000 years. But you can see a kind of dominant cycle here of about 1,000 years, 100,000 years, which is giving us these warm periods in between ice ages over the last 400,000 years or so, and all of the kind of noise of the other cycles coming into play at 40,000 or 20,000 years. So the big question for us, which we'll kind of explore over the next half hour or so, is whether what we're doing to the atmosphere at the moment is enough to keep us from plunging back into the next ice age, which will ordinarily be about time to do that. And the answer is yes, probably we are. So I've looked briefly at some of these external factors, but the main thing that I wanted to talk about now, and for this talk overall, is the internal factors, the composition of the Earth's atmosphere, and how that shapes climate over time. That's mainly to do, the internal factors overall are mainly to do with the composition of the atmosphere and the positions of the continents. So the composition of the atmosphere in terms of the amount of greenhouse gases, current levels of CO2, the dominant gas that controls climate. There are other ones, but they're all kind of indirectly linked to the amount of CO2 in the atmosphere, is about 400 ppm, which isn't a huge amount, except that it has a big impact on how much energy is stored in the atmosphere at any one time. So average global temperature at the moment is about 14 degrees C. If there wasn't any CO2 in the atmosphere, it would be about minus 16. So that amount of CO2 makes the difference of about 32 degrees on global average temperatures. They're small amounts, but they're highly potent in terms of their impact on the amount of energy that's stored in the atmosphere. And the amount of carbon in the atmosphere is determined by a geological carbon cycle, which I'll go through in a moment, but it comprises three interacting parts: terrestrial, which is a fairly small reservoir, and carbon within it is cycled over a period of a few years or decades. A marine carbon cycle, which is a bit bigger, and carbon is cycled through it over a period of thousands of years, and a geological carbon cycle, which is enormous, and carbon is cycled through it over a period of millions of years. So one of the, coming back to what I was saying at the beginning, one of the things that makes climate so complicated is that we're kind of dealing with layers upon layers of spatial timescales and time scales. So spatial scales and time scales layered up over several millions of years ultimately. And unpacking those, given that they're all kind of connected, is quite tricky. So this, I'm not expecting you to read the detail of this obviously, but this in summary is the global carbon cycle, with the atmosphere interchanging carbon with vegetation systems and with the ocean. An ocean reservoir which is layered, the surface ocean that behaves differently to the deep ocean, and that exchanges carbon. And through the weathering of rocks, the atmosphere and the terrestrial carbon cycle bring carbon into the oceans, which eventually is rained out, if you like, in sediments on the ocean floor, which then become part of the geological reservoir over time. But just to go through that in a bit more detail, the three main parts of the geological carbon cycle are the atmosphere, in which carbon resides for perhaps 100 years, actually quite a bit longer. It's got a long tail to it, but on average it's taken us about 100 or 200 years. These are trillion tons of carbon, but you can see this is quite, well, you'll see compared to the other figures that go up, that's quite a small reservoir. The terrestrial carbon cycle holds carbon for a period of months or decades, if you think about, and up to hundreds of years if you think about peat soils and so on, but on average it's cycled fairly quickly through vegetation. The marine carbon cycle holds on to carbon for thousands of years, and you can see it's quite a bit bigger than the other two reservoirs that we've put up so far. And the geological carbon cycle contains about 99.9% of all the carbon on the Earth, and it cycles, or holds on to that carbon over millions of years typically, and you can see that it's dramatically larger than the other ones. And really the essence, if you like, of the current climate change problem is that we're taking carbon that would normally be stored in fossil fuel reserves and so on from the geological carbon cycle, and it would normally take that carbon tens or hundreds of millions of years to get back into the atmosphere, and we're putting it back in over a period of decades. And the question is that likely to kind of have an impact? Yes, very much so. So I need to talk a little bit about how the Earth works and how it cycles that carbon through geological processes. This is a map of the surface of the Earth divided up into the plates. You can see by the yellow lines, the Pacific plate, for example, and the Atlantic divided by the mid-Atlantic ridge. So the surface of the Earth is divided up into these rigid moving blocks of crust and the uppermost bit of the mantle. They're about 100 kilometers thick, and over time they move around the surface. I'll say a bit more about how that works in detail in a moment, but first I just want to talk about the geography of continents and how they've changed and some of the impacts that that's had on climate. So this is a shot from Iceland, the Thingvellir National Park, where you can see, one of the examples where you can see on the left-hand side the east part of the North Atlantic plate, and on the west side on the left, and the east side of the Atlantic plate on the right. So these 6 diagrams just show how continents have moved over the last 200 million years, 250 million years, from having been all gathered together as one continent about 250 million years ago. And they've dispersed over the last 200 million years to the present distribution that we know. And the continents now are more or less as dispersed as they ever have been in the geological record. And over a cycle of about 500 million years or so, continents break up and move apart, come back together again, break up and move apart again. And there's about 3 or 4 supercontinents like this one that we can identify back in the geological record over time. So over the next 250 million years, the continents will kind of coalesce back together again, if you like. Australia will continue chuntering north and eventually glide into China, if you like, completing a kind of mountain belt along that shoreline, and the Atlantic Ocean will again close up in the next kind of 250 million years or so. So Charles Lyell, Scottish geologist, in the 1830s or thereabouts, was speculating along with lots of other geologists about the state of climate. He'd recognised through looking at the geological record that the climate over the last 50 million years or so had been cooling gradually, and came up with this kind of theoretical idea that the world would be relatively hot if the continents were mainly distributed around the equator, and that it would be cold if the continents were mainly distributed around the poles. And that's the same diagram again, with the geography of the continents in the Carboniferous, the so-called icehouse world that geologists refer to, and you can see that it's not perfect, but generally there's a very large mass of continent at the South Pole, and that led to extensive glaciations during that period. And during the Cretaceous, again, it's not perfect, but there's more continent, or much more continental landmass arranged around the equator, and that was one of the factors that gave rise, along with a massive amount of volcanic activity, to the Cretaceous greenhouse world around 100 million years or so ago. So one of the other ways in which continents affect climate is through the opening and closing of ocean gateways. And this example shows that when the Drake Passage opened between South America and Antarctica about 33 million years or so ago, it allowed the circumpolar current to become established. And that has a profound effect on not only regional climate in the south, but global climate, because this current basically prevents heat from the equator getting to Antarctica. And the timing of the opening of the Drake Passage and the buildup of Antarctic ice is closely related. There's some debate about whether the opening of the passage caused the buildup of ice on Antarctica, or whether it just reinforced a cooling trend which was already underway. But either way, it still had a big impact on regional and global climate. Other examples of opening and closing gateways would be the Panama Isthmus between North America and South America. When that closed off, it sort of shut off a global circum-equatorial current and shifted much more the kind of movement from north to south rather than east to west. So that had a fairly significant impact on the onset of the northern hemisphere glaciations about 3 million years ago or so. So this is how the surface of the Earth works, if you like, plate tectonics and volcanic activity. And I'll just kind of talk you through this cycle. It's easiest to start at the Midocean ridge, where two continents being pulled apart reduce the pressure on rocks at depth, and they start to melt. So the easiest analogy for this is, if you think about a bottle of champagne, the liquid is held under pressure when the bottle's unopened. When the bottle's corked, the reduction in pressure allows the gas within the liquid to exsolve. So you change a state from a pure liquid, reduce the pressure into something that becomes a liquid and a gas. Okay, and it's exactly the same thing that's going on 100 kilometers down. If you reduce the pressure, the rock changes from a rock to a rock plus liquid state, and that liquid then rises up towards the surface. And when that liquid erupts towards the surface, the further reduction in pressure allows the magma, the liquid, to give off its gases, which become the atmosphere of the Earth. And one of the most important or dominant gases in eruptions is CO2. So at this mid-ocean ridge, plates move apart, reduction in pressure, melting, and we get magmatism along the mid-ocean ridge and so on, creating these new plates. The plates here are kind of fairly young. They're buoyant, they're hot, they're warm. So these ridges form topographic highs within the ocean basin, maybe 1 or 2 kilometers higher than the surrounding abyssal plains. As the crust moves away from the source, from the center of the ridge, it becomes older and colder and more dense, and gradually kind of subsides to form the abyssal plains of the oceans. The other thing that happens at the mid-ocean ridge itself is this hot magma comes into contact with seawater, which is about 0 degrees C, and the magma is at about 1,000 degrees C, and that sets up an incredibly vigorous hydrothermal circulation throughout the ocean crust. And all of the rocks here become effectively wet. They're kind of not dripping with water, but they're full of hydrous clay minerals and that sort of thing. So when this crust moves away, gets older, colder, more dense and so on, eventually it becomes unstable and begins to sink back down into the mantle. And as it sinks back down, all of the water that was taken on at the mid-ocean ridge effectively gets boiled off as it encounters higher temperatures and higher pressures as it goes back into the Earth. And that water, when it boils off and goes into the overlying bit of mantle, reduces the melting temperature of that bit of mantle, and the magmas rise up and erupt as volcanoes on island arcs, like the Chilean range and around the Ring of Fire around the Pacific Ocean. So it's the volcanism that we're mainly interested in terms of how that affects climate, because if we increase the rate of ocean spreading for some reason and get more magmatism, we'll get more magma erupted at the mid-ocean ridges, and equally, given that the Earth is a constant size, more magmatism here means faster subduction, means more volcanism in these settings as well. So both of those things combined, the rate of volcanism has a significant impact on the climate. So, just to summarize what I've just been saying, the return flux of carbon dioxide, mainly by volcanism, is part of this long-term tectonic part of the geological carbon cycle. And as the volcanisms emit CO2, eventually that will be rained out and is taken up by the weathering of silicate rocks and flushed into the oceans where it gathers in sediments and so on, over again periods of millions of years. One of the other important factors that drives this whole cycle is the evolution of the leaf. So the leaves have evolved about 380 odd million years ago, and when they did so, they gave rise to both a modern hydrological cycle, because of the uptake of water in vegetation and what have you as part of the hydrological cycle. But soil, they also significantly affected soil processes, because dead leaves are basically what makes up soil, together with bits of rock and microbes and so on. But the evolution of the light leaf gave rise to a modern soil processes, which also have an important role in breaking down rocks into their sort of constituent elemental parts, chemical weathering of rocks. So this diagram tracks the relationship between the Earth's temperature and CO2 over the last 600 million years or so. This is derived from some very large computer modeling that geologists started doing back in the early 80s, where they took all of the kind of inputs into that could affect the amount of CO2 in the atmosphere, rates of volcanism over time and such like, together with other evidence from the rock record, to work out the sort of inputs and outputs of carbon into the atmosphere and how that varied over geological time. And the black line is the amount of CO2, and the red line is a kind of proxy measure for the amount of is for temperature over time, basically. The blue lines denote ice ages. So you can see that there's a pretty good similarity between the amount of CO2 in the atmosphere and the temperature. And there are some significant points where things change. One is around 600 million years or thereabouts, where the evolution of organisms with shells drew down a lot of carbon from the atmosphere because there's a new reservoir for it effectively in those forms of life. And the other one I've just spoken about was the evolution of land plants at about 380 million years ago, drew down significant amount of carbon from the atmosphere. And really before that period, any comparisons with the Earth as it is to the way that the Earth as then was are it's like a different planet really, because of the different hydrological and geological systems that are at play. So we can only make meaningful comparisons to today over the last 400 million years or so, when we're talking about similar processes, broadly speaking. The collision of India to Asia over the last 40 million years since India collided with the Himalayas also gives us another good insight into how that's affected climate over the last 40-odd million years. So this map shows the Earth as it was about 100 million years ago, with India well down south of the equator. And over the course of the next 30-odd million years, it sort of raced across north, raced 20-25 centimeters a year, which is pretty quick in geological terms, and eventually collided with Asia. So this just illustrates that northward movement and eventual collision between India and Asia. When it did so, it formed the high Himalayas and also the Tibetan Plateau. So most of the energy and force of the impact is taken up actually with uplifting the Tibetan Plateau. Obviously it has its most dramatic topographic effect in the high Himalayas, the snow-capped ring around here, but Tibet is an area about the size of Europe, elevated to an average elevation of about 5,000 meters. And the combination of this area of uplifted land and the high Himalayas has a dramatic impact on regional and global climate in the area. I'll say a bit more about that in a moment. So this is the Tibetan Plateau, pretty barren place with the Himalayas in the background. So one of the things that Tibet does in creating a large area of land that warms up quite readily during the summer is that it creates a huge amount of rising air over Tibet as a whole. And that draws up moist air from the south from the Arabian Sea, from the Indian Ocean, which falls as rain and snow over the high Himalayas and leaves most of Tibet actually pretty dry because the orographic effect of the Himalayas exhausts most of the rainfall before it's able to get over into Tibet. So the uplift of the Tibetan Plateau basically intensifies the southwest monsoon in India, and the precipitation over the high Himalayas accelerates the rates of chemical weathering of the rocks there, and the chemical weathering of silicate rocks draws CO2 down from the atmosphere. So this process has been primarily what's led to global cooling over the last 40 odd million years or so. And this is basically the same thing again. So in the Geocard model, the model that's used to describe the amount of CO2 in the atmosphere over time, what drives the model is the rate of seafloor spreading, the rate of volcanism, which leads directly to increases in rates of volcanic activity, with CO2 going into the atmosphere. A warmer atmosphere accelerates rates of chemical and weathering of silicate rocks, which draws CO2 back down into the rock reservoir. So there's a kind of a negative feedback cycle with this, where the increase in volcanism gives rise to a warming climate, but the warming climate itself accelerates the rate of weathering of silicate rocks, which then cools, draws CO2 out of the atmosphere. So over a period of millions of years, these things are kind of held in balance. The next kind of illustration of climate is one from fairly close to home. These are pictures from the basaltic rocks on Mull and in Northern Ireland. And in both cases, we find these kind of red horizons. And they're called bowls or laterites, but they're typical of weathering in tropical climates. And you probably noticed that Scotland doesn't have a tropical climate today, or indeed any time around now. And when these rocks were formed about 55 million years ago, it was associated with the Icelandic hotspot as it now is, rising up and accelerating the opening of the North Atlantic Ocean about 55, 60 million years ago. And you can see from these kind of fracture zones across the North Atlantic that the North Atlantic opened east-west. Okay, so there hasn't been much of a change in Scotland's geographical position as a result of the opening of the North Atlantic. But we've got tropical weathering going on, which is a bit odd. And there's a lot of other evidence around this time for the globe being much warmer than it is now. And it's called the Paleocene-Eocene thermal maximum. And it happened about 55 million years ago. And so it lasted about 170,000 years. There was a 9 to 14 degrees C rise in about over a period of about 20,000 years, not evenly distributed, with about 20 degrees C warming at the poles. And atmospheric CO2 levels rose to about 1,000 ppm, so it's just over double what they are now. And sea levels rose by about 10 to 25 meters over this period of time. And it was associated with an injection of carbon into the atmosphere of around about 2 to 7,000 billion tons of carbon. And that took place over about 20,000 years, and then it took about 170,000 for that carbon to be drawn back out of the system. But the thing to keep an eye on is this budget of carbon, 2,000 to 7,000 tons, and the time that it took to do that, about 20,000 years. Because I'll come back to that in a moment. This is a map of what Europe or Northern Europe would look like with a sea level rise of about 10 meters. As you can see, it has a pretty dramatic impact on coastal areas of the UK and the Netherlands. So thinking about the 55 million years ago, we put about, say, 2,000 billion tons of carbon into the atmosphere over a period of 20,000 years. This is the summary of some modelling carried out and published in Nature last year, the early part of last year, which gave rise to some fairly useful rules of thumb in thinking about current climate change. So we have a total budget of about a billion tons, 1,000 billion tons of carbon forever to have a 50-50 chance of avoiding 2 degrees C of warming, which is scientific, notionally the idea of dangerous climate change is any warming above 2 degrees C. So that's the global carbon budget for all time, and we've used up about just over half of that since 1850. And on current trends, we'll use up the rest of it by about 2030. And that's about at the lower end of the budget that we saw for this event 55 million years ago, but it took 20,000 years to get that carbon into the atmosphere then, and it's taken us about 200, 250 so far. So the rate of current climate change is orders of magnitude faster than anything that's gone on in the past. And just to add to that, this diagram shows the amount, the budget, the total budget we have for staying within 2 degrees C warming in the atmosphere, and the amount of fossil fuels that we already know about. This is before people start looking for oil shales and unconventional hydrocarbon sources. Just to illustrate this, more than enough carbon already known about to completely blow the budget for staying within 2 degrees of warming. So one of the big questions that these papers came out at about the same time, but the question was, how do you keep that carbon in the ground and don't burn it? And we haven't been very good at that over the last year, or indeed at all. Historically, this just shows the rate of burning of fossil fuels over the last 150, 200 years or so, associated with the Industrial Revolution and the consequent impacts on global CO2 and temperature over time. I think one of the most disturbing things about this graph really is that for most of the Industrial Revolution was initially powered by water mills, and then steam from burning coal. But even then, over this sort of period from 1850 to 1950, most of the impacts of the Industrial Revolution were quite localized because coal is quite expensive to transport, so you have this kind of coalition, if you like, of natural resources and energy being very locationally specific, and most of the impacts were local or regional of this phase of the Industrial Revolution up until about 1950. What changed after 1950 was effectively the oil economy, which completely transformed the way in which people interacted with natural resources and the environment generally. So what oil and gas allow us to do is to travel into parts of the world that we could never get to. So it's from the 1950s onwards that the rate of use of both fossil fuels and other natural resources begins to kind of intensify exponentially as we have the kind of the reach and the wherewithal to get to the resources, or these resources, that we previously couldn't get to at all. So there's a kind of doubling of the amount of CO2 over sort of a fixed period, with an exponential rise since the 1950s, associated with the burning of fossil fuels. And this slide is just from the recent panel, the International Panel on Climate Change's reports on how long would CO2 released today stay in the atmosphere. And you can see that quite a lot of it's been taken out by terrestrial vegetation and the ocean carbon sink, about 50% to date over the last sort of 150 years or so. But all the signs are that uptake will weaken from the mid part of this century. So beyond 2 degrees of warming, the efficiency of the terrestrial and oceanic sinks begins to reduce. And then so the ocean invasion component will begin to kind of weaken. And then over the longer term, there's a kind of a long tail of CO2 that stays in the atmosphere for potentially thousands of years. And that depends on, crucially, the size of the slug and the rate at which it's input into the atmosphere. So the rate of how big the CO2 slug is and how quickly it's put into the atmosphere really determines how much and how long CO2 stays in the atmosphere over the next 1,000, 2,000, 3,000 years or more. And work related to this question then relates to, so how much is this likely to delay the next ice age, the one that we're sort of more or less due? And at the moment that's sort of been pushed back and back, so I think it's at least 5,000 years off as a result of burning of fossil fuels. That's not necessarily a good thing, by the way. So this last slide just kind of summarizes everything I've said into one diagram. It gets a bit busy because it's all of the area of the globe from the room that we're standing in to the entire surface of the planet on a log scale on the vertical axis, and time to give this talk on the left-hand side to the entire age of the planet on the right. And what I'll do is build up some of the factors that shape weather and climate over different spatial scales and different time scales. So weather systems are typically fairly short-lived. Thunderstorms, for example, last a few hours and over a period of over 2 or 3 kilometers or something like that. And weather systems might be regional, continental in scale, and might last for a few months at a time. There are decadal variations, for example, the El Niño southern oscillations or the North Atlantic equivalents that are decadal by name, and they tend to affect sort of regional and global climate. And they affect things like major droughts and intensity of flooding in tropical countries in particular. There are a number of different forcing factors, for example, the sunspot activity and little ice ages from about 1200 to 1700, or arguably we're still in it, but the effects of it are being masked by emissions of CO2. So they affect climate over centuries and at a regional to global scale. Then the orbital forcing factors that I mentioned right at the beginning shape climate over tens or hundreds of thousands of years globally. And then the positions of continents and plate tectonics and so on shape climate over tens or hundreds of millions of years through the positions of continents and the rates of volcanism and what have you. And if there's land at high latitude, over the poles, that fundamentally determines whether or not we'll have ice ages or not. And one of the things that you can bring out of a diagram like this is that climate is, as I mentioned earlier, this kind of layering of factors operating at different spatial scales and different time scales. But if you want to understand the Earth's climate at a particular spatial scale or time scale, then it's the forcing factors that operate at the same time scale and spatial scale which will be dominant in your understanding of global climate. Except that, normally, oil, coal and gas and fossil fuels and so on would sit in this box here and shape climate over tens or hundreds of millions of years. As a coal bed, for example, gets taken down a subduction zone and gives off its CO2 through volcanism, it would affect climate on that kind of a time scale ordinarily. But what we've done is dug it up and stuffed it into the atmosphere over a period of decades and so on. So the current climate change problem is this short-circuiting of the geological carbon cycle. And it will take tens or hundreds of thousands of years or more for all of that carbon to eventually come out of the atmosphere and for the system to re-equilibrate to some kind of normality. That's it. Global climate change.
questions?
I've got one from Neil. We can come.
From Neil, okay.
So I don't know if I'll say it correctly or whether it's relevant. He was saying that since the last ice age, the optimal climate was, went up 4 degrees some time ago, and so the ice caps must have melted then, but we've still got perhaps polar bears and Arctic alpine plants then, because they're still here. So they must have probably affected when the last ice caps melted.
I don't know. With the short answer, I know that. Yeah, so there was a thermal maximum around 5,000 or 6,000 years ago, coming out of the last ice age. And I don't know what the distribution of that was across the Earth either. So how that affected the polar ice caps, for example, would be in relation to polar bear habitat would be a key question. All this stuff. Jim, George, yeah.
Could you explain to us how postponing the next ice age is a good thing?
How postpone it? Well,
It's not a good thing.
it's not a good thing. Okay. So that kind of leads us into the territory of, how warm or cool do we want the planet to be? Almost it's the same kind of set of questions that lie behind geoengineering solutions to climate. And I think the danger of those is that we know that climate is unevenly distributed across the Earth, and that's good for some people and it's less good for others. So who, if you start thinking about how could we manipulate climate, whether to draw down CO2 to check the current trends, as it were, or to prevent an ice age happening, in a sense that's what we're doing at the moment. The distribution of costs and benefits of that will be, again, highly uneven. Who makes those decisions and whose interest do they make them in? Can't really see a very good way of those questions being answered in the kind of global governance arrangements at the moment, other than by the wealthy and powerful who have all the power anyway. So that's why I've been nervous of it. It's interfering with the natural dynamics of a planet that we don't really fully understand. And apart from the ethical questions of then is, do we actually have a right to interfere in that way? Discuss. George?
One of the earlier slides you showed was of global temperature against time over the last few 100,000 years, and it showed a sequence of ice ages with occasional, much shorter, warmer spells in between.
One of the first slides.
Yeah, one of the first slides. It was interesting because the ice ages, each one went through a number of cycles. It seemed to get progressively colder and colder and colder, and then something switched, and it suddenly went really warm again. It's easy to see there.
It was after this. That one?
Yeah, that one.
Yeah.
See each of the ice ages, see they get progressively colder. Okay, going through a number of oscillations, and then something happens and the switch will come up. What's that pattern? What's going on there? Because each of those ice ages, bar the wee one in the middle, is from the same pattern.
Yeah, well, so I suppose it would depend on how that looks when you spit it out for the 800,000 or 2 million years, really, that cycle's been going on, whether that is a trend or not. I'm not sure.
Each of them is the same, so something must be happening at the coldest point in each one to sort of trigger, tip it back into a warm interglacial. And why is it each ice age gets progressively colder until something happens? I was really just wondering what was actually happening.
Oh, so why is that a gradual descent and that's a sharp out? And
each one of them, bar the short one in the middle of 240.
Okay. Yeah.
Is the same.
Yes, I was reading about something about that last night. I might have to come back to you. That trend is an incredibly complicated one because it's kind of triggered by changes in the orbital characteristics, but then there are all sorts of lags and inertia in the system that take time for the other bits of it to catch up. But that one is again a shift in the orbital characteristics, but it drives it more quickly. But there is a good reason for it, better than the one I've just explained. But it's quite complicated. I'll come back to you. You have a question, did you?
Did you actually ask me a question? Well, I'll
Oh.
come up with another one because I was just thinking about ocean acidification.
Yes.
Changing temperature and more acid and that breakdown of carbon, which release more carbon into the system, and there's like a negative feedback.
Positive, yeah.
Positive feedback.
Yeah.
Thank you. Positive feedback. So I mean that's just one. Is there any other cycles like that that have this positive feedback? So is there just a little program and then triple things once?
Okay, so maybe just to explain for some others who maybe didn't hear that, or there's the oceans and the atmosphere for carbon, for the sake of carbon, are kind of in equilibrium, at least over a few hundred years and so on. So increasing CO2 in the atmosphere leads to increasing CO2 in the oceans. And as oceans warm, water holds less CO2 than warm water holds less CO2 than cold water. So as the oceans warm, they release more CO2, which further drives warming. One of the other feedback, I did kind of mention a feedback. There are lots of these, and that's another reason why climate is not easy. But where would it be? About here. So. That one. Yeah, so this is a positive and a negative feedback. So if you had some of the people who theorized initially about this kind of rock weathering cycle, the uplift of the Himalayas, accelerating chemical and rock weathering, would result in this kind of drawdown of CO2. Which would, hang on, let me think. These are always hard to get your head around. So the increase in rock weathering with the uplift of the Himalayas would draw CO2 down into the oceans. The cooler climate, and this would be a negative feedback as well, the cooler climate would decelerate rates of chemical weathering, which would increase CO2 in the atmosphere and keep that as a kind of negative feedback. And likewise, this volcanism thing, increasing CO2 from volcanism increases CO2 in the atmosphere, but the increase in rock weathering keeps that in check, so that's a negative feedback. So examples of positive feedback, sorry, just to answer your question simply, would be the increasing global temperatures and reducing sea ice at the Arctic replaces white stuff with water, which is kind of black stuff really. So that leads to more absorption of solar radiation in Arctic waters, which leads to more warming. So that the decreasing albedo becomes a positive feedback. So yeah, and all the this is one of the areas that's quite difficult for climate modelers in the IPCC, and so for example, long-term release of methane and so on isn't factored into a lot of the climate change models at the moment because nobody's quite sure how or when that will work. Likewise, changes in the North Atlantic Oscillation and regional cooling around the North Atlantic as an aspect of warming. Nobody quite knows when that will happen and how it will work, so that's excluded from the models. But all the indications are that the net feedbacks are positive. So when you add those back into the models, they all get a bit worse in terms of what climate change looks like for different degrees of warming, 2, 3, 4 degrees and so on. So yeah, there's quite a lot of those feedbacks, and the way that they interact is quite complicated, as you can imagine.
So it makes modelling very hard.
Pardon?
It makes modelling very hard to predict.
Yes, that's right. Yeah, which is again why the kind of geoengineering, whether it's sensible to try and keep us out of an ice age, is difficult because we just don't understand the science behind it and what the consequences of that would be. Julia?
So if we manage to limit our emissions to that 1,000 gigatons,
Yes.
is it, or below, then we don't emit any more additional CO2 or carbon, then the planet will just start to hopefully equilibrate. Is that?
Well, theoretically, yes, it would. So, but that is actually quite difficult because that's 1,000 gigatons for all time, right? And some of the emissions from land use and land use change, are going to be very difficult to keep to zero because we need to eat. So as soon as more or less you put a spade in the ground, you're affecting that part of the cycle. So, all the indications of the modelling that's been done so far for current climate change emissions budgets and things like that suggest that by the time you're kind of talking about 80-90% reductions, it's really hard to get at those last 10-20% reductions because they're things associated with eating and breathing which are difficult to kind of avoid. The question then would be how the rate. It's the rate of, if you could get that down to that kind of a level, it would be a slower process, and there would be more chance of the Earth kind of equilibrating to that system. The additional inputs from burning fossil fuels and so on that's the big part of the budget question at the moment, carbon budget question. But it would still take several thousand years probably for the system to kind of get back into its normal rhythm. David I've got a question for you really, which David was asking if you found this or the idea of having these lunchtime seminars interesting, would that be something that would be worth trying to arrange on a regular basis? Yeah. Okay. We'll try and work out something.
Well, we've gone to the film and stuff, so the hope is that we'll maybe try and get it on the internet or something like that, so that other people can see this as well.
Okay.
You agree to it?